Hi guys, Miss Peterson here, and welcome to AP Physics 2, Lecture 4-4, all about RC circuits. So in this lecture, we're going to be talking about what an RC circuit is and how RC circuits, or resistor-capacitor circuits, not remote control, work as they start charging. The capacitor becomes fully charged and reaches what we call steady state. Okay. So we're actually going to start this out with a demonstration. Okay, first where we have a battery and a resistor and a capacitor in series. Now, once this switch right here is closed, what do you think is going to happen to the current in the circuit? What do you think is going to happen to the potential difference or the voltage across R1? Okay. What do you think is going to happen to that voltage? What do you think is going to happen to the voltage across the capacitor? Okay, let's go ahead and look at it. So here I have that circuit set up currently with the switch open. Okay, so I'm going to go ahead and close the switch, and I want you guys to watch what happens to the voltage across the resistor, the capacitor, and to the current in the circuit. So we close that switch. Okay, going to go ahead and pause it right there. So zooming in right here on this graph, across the resistor, we see that the voltage across it automatically jumped up to about 3 volts, that same of our battery. And then it started to decrease, where the capacitor did the opposite, okay? It started out at 0 and then gradually increased until it got to about 3. And for the current in the circuit, we can see it jumped up to about 0.3 and then gradually decreased, okay? This resistor had a value of 10 ohms, so the total resistance was 10 with our 3-volt battery. 3 divided by 10 gives us that 0.3 amps of current. And why that happens is that immediately after we close the switch, okay, the current through R1 is going to be equal to that voltage of the battery divided by R1, okay, because that's going to be the total resistance, okay, equals the current going through that resistor 1. It's a series circuit, so that really is the total current, okay. Now, that's going to be immediately after the switch is closed, and then it will gradually approach 0 at the end, okay, at what we call steady state. Okay, because once this capacitor is fully charged, I'll let it play for a little so we can see that. Okay, and you can even see it in those electrons. They're not moving anymore. There's no more current flowing in the circuit because that capacitor is fully charged and has blocked the flow of current. Okay, so the current flowing through the capacitor R1, it's a series circuit, so that will be the same. Okay, so it will be the same as all of there. It'll start at some total current and approach 0. Now, for the potential difference across R1, okay, what you saw that immediately after that switch is closed, the capacitor acts like a wire. So immediately after the switch is closed, okay, this potential difference is going to be equal to that of the battery. So at first, okay, immediately after the switch is closed, delta V for R1 will equal the voltage change of the battery. But after a long time, okay, it will approach 0. Where across the capacitor, we saw the opposite, okay? Across that capacitor, we saw the voltage. See, can I scroll that over? Nope. But you can see how the voltage was increasing in that part. It was decreasing on the resistor and increasing across the capacitor. So across the capacitor, it would go from 0 to the voltage of that battery. Okay, so that charge will build up. The charge will start at 0 and will build up to, well, our main equation for capacitance is, or Q equals delta V times C. So it'll build up to the voltage of the battery to Q total, which will be the voltage of the battery times its capacitance. Okay, cool? Okay, cool. But how does that work if we hooked it up in parallel? Let's go ahead and look at that one. Okay, so here in this parallel circuit, we can track the total current coming out of the battery, the voltage across the bulb. I changed it out to a bulb for this one so you can see how the power or the brightness of that bulb changes as that capacitor charges. And then we have the voltage across the capacitor. So go ahead and make your predictions. What do you think is going to happen when I close this switch? And let's go ahead and do it. Make sure this is on there. So we see that current almost immediately jump up, okay? And then we see that discharging through the battery. Okay, let's go ahead and look at that one more time. To make it a little bit slower, I'm going to add a resistor here with the capacitor, just so the change is a little slower and you guys can see what's going on there, okay? So I'm still just measuring the voltage across the capacitor, but I added that resistor in there so we get a little bit slower change. Okay, let's go ahead and close that switch. And there we go. We see immediately the voltage of that battery jump up and that voltage of the capacitor climbs. Okay, for this one, we see its current stays at a super low or negative range, okay, about -1. Where when I didn't have that resistor in there, okay, take that back out of there, close that circuit up, we can see that the capacitor will still become fully charged, okay, equal to that of the battery. If I go ahead and pause this and discharge that capacitor, oh, animation speed limit reached, okay, discharge, okay, we can still see that voltage. The voltage is going to jump up immediately, okay, due to that capacitor. Then eventually, once that capacitor is fully charged, we have no more current flowing in this top branch of the circuit, and it's still cycling through that light bulb, okay? So for the current going through R1, okay, in this circuit, as soon as the switch is closed, okay, all of that current will be going, or the capacitor will act like a wire. So all of the current will just be going in that loop with the capacitor. So the current will be 0 at first, okay? It is a short circuit. And then as time goes on, it will approach the total current. The total current in the battery, okay? There would be no more current flowing in this path once it's fully charged. So the total current would just be the voltage of the battery divided by that resistor, okay? Where the current going through C1, initially it is just that total current. So it's like infinite amount of current immediately, okay? It's just all flowing there. There's like no resistance. So it starts out like crazy high, okay? And then as that capacitor charges, its resistance increases. So it approaches 0, okay? Now for the potential difference across R1, well, the whole time it's connected to the battery. So it's going to be equal to the voltage of the battery the whole time because it's connected directly to the battery, just like the capacitor. The delta voltage across the capacitor will also equal that voltage of the battery the whole time. Okay. It will take if in this like hypothetical circuit, because we have that current at infinity, basically, okay, because the resistance is 0. So current is voltage over resistance. If the resistance is 0, current approaches infinity. But for that just happens for like a brief second, and then as it charges, it'll charge up to that voltage of the battery. Okay, but it happens really quick unless there is a resistor in series with it to slow that process down. And for the charge stored on C1, okay, basically immediately it will be equal to the voltage of the battery times that capacitance. Okay, cool? Okay, cool. So that's an RC circuit. When we're charging a capacitor immediately after the switch is closed, the capacitor will act like a wire. Okay, so when you have more resistance in a circuit, it's going to take longer for that capacitor to charge. Okay, and immediately it's like that, and then once it's fully charged, we say that circuit has reached steady state, so the values of its voltages and currents won't be changing. Okay, when it is in steady state, the capacitor acts like an open switch. Okay, its resistance is approximately equal to like infinity. Okay, because it has that built-up electric field to prevent the flow of charge flowing through it, and no current will flow in the branch containing the capacitor. Now, in the AP curriculum, you will only need to analyze RC circuits either immediately after they're connected or in steady state. You do not need to worry about the voltage or the current in that in-between state. While you should have a conceptual understanding of what's going on, you do not need to know the mathematical equations for that. Okay, so let's just go ahead and practice analyzing some circuits. Starting with this one, okay? Now, okay, as soon as the switch is closed, okay, remember the capacitor acts like a wire. Okay, so C, capacitor, like a wire. So I actually prefer to redraw the circuits in that state. So immediately, if the capacitor is acting like a wire, okay, we would just have that 12-volt battery and the 6 ohm resistor in parallel with the 3 ohm resistor. And we just have a simple circuit there. Immediately after that switch is closed, no voltage or no potential difference is built up across that capacitor yet, so we don't have any charge stored on it yet. For these ones, they're both connected directly to the battery, so the total voltage is going to be the voltage on each of them. It just becomes a simple circuit for us to solve. Okay, if we know the voltage and the resistance, we can use V equals IR to find that current. 12 divided by 3 is 4 amps in this path. 4 amps in that path and 2 amps in this path. Okay, for a total of 6 amps of current going into the battery. So then 12 divided by 6 gives us that total resistance of 2 ohms, which again, you could also find from 1 over R total equals 1 over 6 plus 1 over 3. Okay. Now, in steady state, a long time later, the capacitor is going to act like an open switch. So, I'll just call it steady state. In steady state, we still have that 6 ohm resistor, okay? And we have that 3 ohm resistor, but then it's like having an open switch there for the capacitor. Okay? So we can tell, because of that open switch, the capacitor acting like an open switch, no current is going to be flowing in that path. So the current going through the 3 ohm resistor would be 0, meaning there's no voltage across it either. Okay, but we still have the 2 terminals of the switch here that are connect that spot. Okay, so the voltage across that switch, across the capacitor, will be equal to that 12 volts. Okay, so using the base equation for capacitance, which is, I believe, delta V equals Q over C. Okay, delta V equals Q divided by C. We can calculate that we have 6 times 10 to the negative 3 coulombs of charge stored on that capacitor. Okay, solving out the rest of the circuit for that 6 volts, its voltage across it still hasn't changed. So we got 12 volts and 2 amps of current. But now, since there's no current flowing here, there's only that single path for current to flow. So that's also going to be the total voltage and the total resistance. Okay, cool. Okay, cool. Now, one other thing I want to talk about is just how to redraw these circuits, because it does change a little bit. This one, because we switch and the open capacitor, well, if it's in steady state, the capacitor just acts like an open switch. So the switch closed, but then the capacitor acts like an open switch. So this is one of the examples where the capacitor is really just changing the behavior of the circuit and which elements are in series and which elements are in parallel, rather than actually participating in that circuit. Because we're not going to have a voltage difference across it in either state. And let me go ahead and show you that, because that is part of the confusing, one of the hard parts of this is just figuring out what this circuit would look like when the capacitor or acts like a wire versus when it acts like a switch. Okay, so let's go ahead and start with as soon as the switch is closed. Okay, so as soon as the switch is closed, this path is going to act like a wire. So let's redraw the circuit considering that path as a wire. So we got our 20-volt battery. Okay, and then coming out, and then we have a junction here. And at that junction, we can either go to the 6 ohm resistor or to that 12 ohm resistor. So I'm going to redraw it and make that super clear. Okay, so it can go to the 6 ohm resistor or the 12 ohm resistor. Okay, and then after it goes through those resistors at these 2 points, it can either go to that 4 ohm or to the 8 ohm. Okay, it's another junction because that switch is just like a wire. So it comes together, and then again, it can either split and go to the 4 ohm resistor or the 8 ohm resistor. And we have this circuit to solve. Okay, so let's go ahead and solve this circuit. I think the easiest way here is going to be to combine these two that are in parallel and make a simple series circuit. So let's go ahead. RC circuits are a great review of just solving circuits. So if I were to combine these two resistors, I would do 1 over R total equals 1 over 6 plus 1 over 12. Okay, and I would get that our total then is equal to 4 ohms. Okay. Then for the other one, okay, I have a 4 and an 8 ohm resistor. Okay, so I would have 1 over R total equals 1/4 plus 1/8. So that's like 3 over 4 is our total. So 4 over 3, 1 over 4 plus 1 over 8, 1 over, yep, cool. So 3/8 or whatever, it comes out to 2 and 2/3 or 2.666666, I'll say 2.67 ohms. So that is our equivalent circuit in a simple form. Okay, we can tell there then that the total resistance, okay, our total is just going to be 4 plus 2.67, so 6.67. Okay, and then we know that total voltage is, of course, the 20 volts. So the total current flow in here will be 20 volts divided by 6.67 ohms, which gives us about 3 amps of current. Yep, 2.9999, so 3 amps of current flowing. Okay, that is the total current flowing in the circuit. So for the voltage, okay, the voltage drop from there would be equal to that 20 volts divided by 4 ohms, so a 5-volt potential difference. Now remember, this 4 ohms is really this 6 and this 12 ohms. So, wait, 20, oh, I know how to math. That's not how I do it. V equals IR. So I have 3 amps times 4 ohms for a total of 12 volts. Now remember, this 4 ohm resistor is actually here and here. So that tells us that across our 6 ohm resistor and across our 12 ohm resistor, we have 12 volts. Okay, which means 20 minus 12, we must have 8 volts across that one. And you could also check it from 2.67 times that 3 amps. Okay, 2.66667 times 3 gives us 8 volts. Okay, so we can use those to find the currents. Okay, V equals IR. So current is just voltage divided by resistance. We got 2 amps flowing here and 1 amp flowing there for a total of 3 amps. Okay, and then it gets split here into 1 amp through the 8 ohm resistor, 2 amps through that 4 ohm resistor. Okay, and we've solved our circuit. Now, in steady state, a long time later, let's go ahead and draw that circuit. Also, for the capacitor, one of the ways that you can understand that voltage difference is by looking at where that voltage difference is. So it is across the 6 and the 12 ohm, in between the 6 and the 12 ohm. And we can see that there's no potential difference there after the 6 ohm and after the 12 ohm resistor. Okay. Now, let's go ahead and talk about steady state. So once that happens, then, okay, it's kind of like this path in the middle doesn't exist, okay, because it is acting as a fully charged capacitor. So to redraw that circuit, we got our 20-volt battery. Okay, we got this junction where we could go to the 6 ohm and the 4 ohm resistor before it comes back together. And this one would go through the 12 ohm and the 8 ohm. Okay. Now, the capacitor is in between the 6 and the 12. Okay, so that capacitor is on those two junctions. Let's see if there will be a potential difference across it there. Okay, so we got 20 volts. If I'm going to simplify this circuit, okay, I would make it a simple parallel circuit. So I got the 20 volts, and then it's going to a 10 ohm resistor. Okay, 6 plus 4, 12 plus 8 is 20. So a 20 ohm down at the bottom. And now we just have a simple parallel circuit. Okay, let's go ahead and zoom on in here. So in this circuit, the voltage difference across each of these will be equal to 20. So that tells us that we have 20 divided by 10. So 2 amps of current flowing here, which remember is this point. So 2 amps, and 20 divided by 20, 1 amp flowing through this path. Okay, so we can add that to our chart. Through the 6 and the 4 ohm resistor, we have 2 amps of current. And through the 12 and the 8 ohm resistor, we have 1 amp of current. Okay, and you might notice that this is the same as this, which we would expect. Okay, the steady state is going to be identical because of how that switch behaves. Okay, so we got 12 volts and, so 6 times 2, 12 volts potential difference there. 4 times 2, 8 volts there. 12 times 1, 12 volts there. 8 times 1, 8 volts there. So our voltage drop across the 6 ohm resistor is 12 volts, meaning the potential here, 20 minus 12, is at 8 volts. Potential difference across this 12 ohm resistor is also 12 volts. So that point is also at 8 volts. There's going to be still no charge stored on the capacitor. Bit of a useless circuit. Since that total current is at 3 amps, we can tell that total resistance is going to be the same. Okay, cool. Okay, cool. While the AP Physics 2 curriculum doesn't have you actually calculate the voltage or the current at any time during charging or discharging, we do need to understand conceptually how that happens and be able to do some basic calculations, including something called the time constant. So it makes sense that as that charge builds up on the capacitor, the current is going to decrease, okay? Those charges are building up. They're going to be repelling the electrons that are trying to move around. So yeah, it makes sense that that will decrease. And of course, when it's the reverse, it is an exponential increase. Now, this rate is determined by something called the time constant, which is given the lowercase letter tau. Okay, and the time constant equals RC for our RC circuits, where R is going to be the equivalent resistance in our circuit, and C is going to be the capacitance. Okay, now if we're looking at these graphs right here, okay, they give us our time in seconds. So our time constant is in units of seconds. And you can note it's not just like how long it takes to time. It actually becomes fully charged, okay, or fully discharged, okay, at about 5t. Now, this is an exponential equation. Again, like I said, you don't need to know it, but it is helpful to know that it takes 5 time constants to fully charge or discharge. And that's to get to like that 99 point whatever percent that it gets to. And it does get pretty close to there by 4 time constants, as you can see. Okay, now let's go ahead and look at how those units work out real quick, because it does seem a little funky that we're multiplying resistance by capacitance and then we're ending up with seconds. Okay, so if we think about this, okay, do it off to the side here. Tau, our time constant, equals resistance times capacitance. Now, resistance, remember, is a measure of that voltage and a current. If we're looking at V equals IR, that resistance is how many volts of energy that can flow for each how many amps of current can flow given that voltage. So we can think of its units as the volts per amps, okay? And then capacitance, we know, is how much charge you can store per volt. So that's going to be our coulombs per volt, okay? We see our volts cancel out. So we have coulombs per amps. And then we know amps is current, which is charge over time. So we could represent amps as coulombs per second. We see those cancel out, and we end up with seconds at -1 on the bottom. So it is in units of seconds. And again, that is when the resistance is in ohms and the capacitance is in farads. Now, a higher resistance or a higher capacitance means a longer charging time. Why does that make sense? Well, obviously, okay, both of those things, higher resistance would mean a slower current. So it's going to take longer to deposit all of that current on the capacitor, where a higher capacitance means more charge. Okay, so you're going to need more current or more charge for that time. Okay, so both of those means a longer charging time, a higher time constant, but again, it's just based on how quickly those charge builds up. Yep. Now, the actual graph and equation for it does look like this, where if we wanted to calculate the charge on a capacitor, we use that CV equation, but then we would multiply it by a factor where it's 1 minus the exponential determination of the time constant of the time divided by RC, which again, RC is that time constant tau. Okay, so, but again, the AP Physics curriculum will not ask you to do things. It will only ask you about the beginning and the end. So at 0 time constants, okay, that means we have the maximum amount of current, okay, the current is at its max. That means that the resistor will have all of the voltage of the battery, and the capacitor will have a charge of 0, okay, because it hasn't been fully charged yet, okay? So when we get to the end, okay, our current will be basically 0. The capacitor is where all of that potential difference will be, okay? And the charge on the capacitor will be equal to that max charge. Okay, cool? Okay, cool. Let's go ahead and do one example problem. So we have 2 simple circuits, okay? Each consists of a 9-volt battery, a capacitor, and a resistor. Okay, so the simplest of RC circuits. Okay, we have a 10 millifarad. Oh, I think that's supposed to be micro. Okay, micro is more reasonable for it, but you know, it's written as millifarads, so we're just gonna go with millifarads. Okay, in circuit A, the resistor has a value of 10 ohms, while in circuit B, it has a value of 10 kiloohms. Okay, how do the time constants compare, and how long will it take the capacitor to be fully charged in each circuit? So how does this changing that factor, okay, we're changing it by a factor of 3, how does changing that factor of the resistance really affect that circuit? So let's go ahead. We have our variables. So let's go time constant for circuit A. Millifarads, that's going to be 0.001 farads. So we have the tau constant is RC. So for circuit A, we have 10 ohms times 0.001 farads, okay, which gives us a value of, I should be able to do this in my head, I'm pretty sure it's 0.1. Okay, 0.01, we know this, 0.01 seconds, where the time constant for circuit B will be 10,000 ohms times the 0.001 farads, because it's 10 kiloohms, which gives us a value of 10 seconds. Okay, so those are the time constants for B. So for fully charged, we say it takes approximately 5 time constants. So for circuit A, that would happen in 0.05 seconds, where for circuit B, it would take 50 seconds. Okay, so 0.05. So because we had 1,000 times the resistance, we have 1,000 times the time that it takes to charge. Okay. Okay, cool. Okay, cool. That's it for RC circuits.